In this video, we'll be taking a look at model evaluation using KFold cross-validation. This is a more rigorous approach to model validation in comparison to a simple train and test split. We'll be looking at a bivariate example with roughly about 100 data points, as you can see on the screen. We'll be evaluating three different models. One, which is a linear model, then a quadratic polynomial, and finally a piecewise linear function. If we were not to do any kind of model evaluation, then we simply wouldn't know which one of these models would generalize well to new data. In five-fold cross-validation, what we do is we randomly split our data into 5 different mutually exclusive folds. We hold out one of the folds, which is 20% of the data, as our test data set, and the remaining 4 folds, which comprises 80% of the data, is our training data set. We fit our models to the training data set and then bring in our test data set and evaluate the performance of each one of these models. We can measure the residuals and the squared errors, and we keep that aside. We then look at the second fold and treat that as our test data, while the remaining 80% is going to be our training data. We do the same thing as we did before and compute the errors against the second fold test data. We repeat this with the third fold as our test data. And then the fourth fold as our test data. And finally, with the fifth fold as our test data. So we're going to get 5 model fits for each one of these different models and the corresponding squared errors against the test data. Now we can combine the results and look at the performance of the linear model. We get an average squared error corresponding to the fits. Then we look at the quadratic polynomial, and across all of the 5 folds we can compute the average mean squared error or squared error. And finally, for the piecewise linear function, we again average out the performance across each one of the 5 folds. We put all of these results together and we see that the quadratic polynomial averages the best performance across each one of the 5 folds with the lowest error. But what's more important is that the standard deviation of the performance of the quadratic polynomial is the least, which means that it varies the least across each one of the 5 folds, indicating that the quadratic polynomial is less sensitive to the choice of test and training data in amongst the 5 folds, and therefore is the best model to generalize to new data. And so just to recap, what we do with KFold cross-validation, K is typically 5 or 10. We split the data into mutually exclusive K equally sized folds, and this selection happens randomly. Each fold serves as test sets exactly once, while the remaining folds all serve as training data. One of the advantages of KFold cross-validation is that we not only get a measure of the average performance across all of the K folds, but we also get a measure of the variability of the model performance across all of the K folds. In general, you are seeking a model that exhibits low variability across all of the K folds. This indicates that the model is not sensitive to the choice of test and training data in the entire dataset, and therefore probably is the best model to generalize to new data.